Okay, yeah. Hello everyone, I'm Ishan, and today I'll be presenting my PhD dissertation titled Towards Label Efficiency and Privacy Preservation in Video Understanding. So a bit about myself, I joined PhD program in fall 2019, advised by Dr. Mubarak Shah at CRCV Lab. And during my PhD journey, I was also got opportunity to intern at Adobe and Apple. So I'm from Gandhinagar, which is on left side of, west side of the India. And so yeah, let's begin with some background in video understanding. Video understanding involves like analyzing spatio-temporal interactions such as like human body movement or hand-object interactions. So this includes some of the known action recognition tasks or where videos are categorized based on the specific actions, or it may also extend to like uh, the, actually there is some lag the screen and okay, and it could be also extend to identifying multiple attributes like scene objects and within videos, or even focusing on like low level tasks such as video object segmentation. So on various video understanding tasks, supervised learning has achieved like success. However, this success comes at the heavy cost of extensive labeling. For example, some large-scale label data sets are kinetics 400 something something V2 or hex, and annotating such data set requires enormous human efforts, and that's why it's expensive to annotate at larger scales, and which limits the progress in supervised learning. Meanwhile, the volume of video data continues to grow exponentially over internet. As we know, like 50% of data on internet is videos. And to leverage this kind of unlabeled data, there are two major learning paradigms come into the picture. One is self-supervised learning, which leverages purely unlabeled data. And another is semi-supervised learning, which deals with the smaller scale of labeled data along with the unlabeled set. So self-supervised learning allows model to learn from purely unlabeled data, and such learned representations could be useful in many downstream tasks such as action recognition or video object segmentation. On the other hand, semi-supervised learning, a small labeled data set is also provided along with the large unlabeled data set, which is more practical setting because we always have like small scale of label class defined. And so semi-supervised learning is often applied to like some specific task, like for example, action recognition. So previous slides we discussed only about like the efficiency in in video understanding, but there is another concern of like privacy preservation. In video analysis, like there are like growing concerns such as like personal attributes, for example, like clothing, gender, or other sensitive features, like for example, hairstyle, or it can be exposed to like video understanding algorithm, which is undesirable. And current methods for privacy preservation, they need this kind of attributes frame-wise, which we know like it's very infeasible to annotate such attributes frame by frame. And so there is like a strong need of label efficiency there as well. So now that we understand the urgency and importance of label efficiency and privacy preservation, now I'll outline the structure of this discussion. So we'll start with Tickler, which is a self-supervised framework based on contrastive learning, and it achieves like strong results on high-level tasks such as action recognition, but it doesn't perform well on like low-level tasks, for example, video object segmentation or tracking. To address this problem, we introduced no more shortcut, a method which is based on temporal pretext tasks. And it excels both on like high-level and low-level tasks. So while both of these self-supervised method, they are fine for like learning from unlabeled data, it provide the best solution for whenever a small scale of labeled data available. So this led us to explore like a semi-supervised framework called time balance. So in time balance, it combines like strength of both video self-supervised models, and it achieves state-of-the-art results, but that only on coarse-grained actions, and it doesn't perform well on fine-grained action. So for fine-grained action, we recently developed a fine pseudo, which leverages like learnable temporal alignability, and it demonstrates best results across both fine-grained and coarse-grained data sets. And it also enables capability of learning from like open world setup as well. And finally, to address the privacy concerns in label efficient manner, I'll cover SPACT, which operates without requiring any private attribute labels. So yeah, starting with the Tickler, which was published in CVIU in 2022. So Tickler is self-supervised learning framework where we propose like two novel temporal contrastive losses. And it is evaluated on multiple downstream tasks such as action recognition and video retrieval. And it works, provides strong results on that. So before diving into our proposed temporal contrastive losses, let's first review some fundamentals of contrastive loss. So one of the most commonly used framework is Sinclair, and which was from Hinton, and which works by maximizing the mutual information between the two augmented views of the same image instance, and by repelling the views of the different instances. So extension of SimScalar works effectively for videos. We can think in terms of like taking clips from like video and increasing mutual information between them, while decreasing the mutual information between the clips from the other instances. So putting it into the equation form, we can see like in the numerator, we have the clips from the same instance, I, and negatives are coming from different instance, J. And this similarity function is nothing but like taking softmax over the cosine similarity. And it works well, but it faces like an important issue of like temporal invariance. So let's understand like this temporal invariance through this example of long jump action. So in this action, we can see the first clip of the action, it consists of like the running sub action, and the second clip, it includes like a jumping action. So according to this kind of extension, it tries to learn the similarity between these two clips. So which is quite counterintuitive, and it underutilizes the motion information provided in the video. So research question is that, can we overcome this limitation by introducing new contrastive losses? So with this motivation, we propose Stickler framework, which encourages temporal diversity at two levels. First at clip level and second is at the temporal pooling of the features. So starting with the first loss called local to local temporal contrastive loss, and which introduces a diversity at the clip level. So let me walk through this by step. And from this video, from any video, we first sample like 4 non-overlapping local clips shown in different color segments here, and pass each of the segments through like different two sets of augmentations. And so it produces like two distinct views and similar to the regular contrastive loss. And next we pass each of these clips through 3D CNN and MLP and project them into like a low dimensional representation space. So now taking this first clip as an anchor, we see that this GI prime clip, it's temporally aligned because it's coming from the same timestamp, and the other clips are temporally misaligned. So we can formulate contrastive loss by treating the temporally aligned clips as the positive, shown in the green arrow, and temporally misaligned clips as the negatives, shown in the red arrows. So in equation form, we can, we can see that like, the temporally aligned clip is in the numerator and misaligned clips are in the denominator, similar to the regular contrastive loss. Now let's look at the second proposed contrastive loss called global to local temporal contrastive loss. So previously we discussed introducing temporal diversity at clip level, but in this loss we will aim to introduce temporal diversity at the feature level before temporal pooling layers. So similar to the previous contrastive loss, we sample like two clips here. Like, we sample 4 non-overlapping clips, pass it through the 3D CNN, and take its temporal pooling and pass it through the projection layer to get the representation, which is like we are repeating the same process here. And additionally, we also sample a global clip as well, which encompasses all these local clips, and pass it through this same 3D CNN and obtain feature maps. So now here, instead of taking temporal pooling, we pass each of the temporal slice through projection heads and obtaining their local representations. So if we backtrack a little bit, like we can see this local representation, it is temporally aligned with this global representation of the local clip here. And yeah, so by using this observation, we will formulate the temporal contrastive loss similarly, in which like temporally aligned segments are positive, shown in the green arrow, and temporally misaligned segments are negative, shown in the red arrows. And putting this into the equation, we see like it has the reciprocal kind of like negatives here, global to local and local to global. So we compare our method with prior video SSL approach, and as we can see, like it's very highly active and competitive research area. And to ensure like fair comparison, we use like the standard setting of 16 frames and 224 resolution, 112 resolution. And we report performance on like after doing self-supervised pre-training on one dataset and fine-tuning on another dataset. So starting with UCF 101 to another split of UCF 101, then UCF 101 to HMDB, kinetics to UCF 101, and kinetics to HMDB. So as we can see, like Tickler outperforms all prior methods across all different settings. And we also report results on zero-shot video-to-video retrieval, where no fine-tuning is done after self-supervised pre-training. And results are reported in terms of like top 1 recall rate and through the top 20 recall rate. And we see like further improvements, like more significant compared to the fine-tuning. So in summary, we propose 2 novel temporal contrastive losses, and Tickler outperforms, the prior work and performs competitively on various high-level downstream tasks. And it demonstrates that like introducing temporal diversity, it helps in video self-supervised learning, and it gained a lot of traction in the community and gained over like 180 citations, and our code base is publicly available. So we have seen like Tickler is more suitable for like high-level recognition tasks, such as like video-to-video retrieval or action recognition. However, it doesn't perform well on like low-level temporal correspondence tasks. So what I mean by that is like it's a kind of tracking task where the mask of the first frame is given and we need to track it throughout the video. So Tickler doesn't produce like effective solution for this kind of low-level task. And another application is like in pose propagation, where we need to track the key points of the person's pose. So to deal with this limitation, we propose no more shortcuts, published in AAAI 24. It was part of my internship at Adobe as well. And so the main difference between Tickler and this method is that this is based on temporal pretext tasks, whereas Tickler was relying on contrastive learning. And so here we introduce like 2 new frame level temporal pretext tasks, which effectively break shortcuts in the existing task. And this approach like performs well on both high level and low level temporal correspondence tasks. And for example, some low level tasks could be video object segmentation or pose tracking. So yeah, before moving into our contributions, let's review like what is temporal pretext task. So temporal pretext task is like solving a puzzle, and by solving that puzzle, a model learns like a useful generic spatial temporal representation. So some of the tasks includes like, for example, it could be temporal order verification, where we need to identify if the frame is in order, or like if the sequence consists like out of order frames. Or it could also include some of the playback speed prediction task as well, where model classifies the playback rate of the video. So yeah, so first we will take a closer look at the existing pretext task and understand what's preventing them to learn like more meaningful representations. So in this original sequence, from the video, it is well known to take like a frame consistent cropping, which is like selecting a region and cropping the same region across the sequence. So it is well known practice. So now, when we consider tasks like, let's say we are just considering tasks where we need to identify which frame is out of order. So while solving this kind of task, we expect model to learn both like global and local motions and like a high level temporal correspondence out of that. But for example, like how actor moves through the video and how her body joints like corresponds to from frame to frame. So there is a problem arise like when we focus on a local area here. For example, when we just focus on this yellow highlighted region as shown here, we can see a sudden change here, right? Like in the out of order frame. So we don't really need to look into like the whole actor. Like we can just look into this like local patch and solve the task. So in a way, this is kind of shortcut we are saying, and it hinders learning the spatiotemporal features in self-supervised representations. So that was our major contribution, that we identify that shortcut, and after identifying that local patch-based shortcuts, we break it through like simple spatial jittering of the each frames. So as I mentioned previously, we are taking like frame consistent cropping in the regular video, which was a standard practice. But instead of doing that, we do like a spatial jittering, which is like frame independent cropping in each frame of the sequence. So as a result, we can see like we can't solve the task by looking at a local patch here, right? Like, I mean, every patch is like, it doesn't provides a correspondence by just looking at the local patch. So to solve this kind of task, we really need to look into like high level features of the actor, like how her body joints move through the sequence. So yeah, after identifying and resolving the shortcuts, we also propose like two temporal pretext tasks as well. So previously, all of the temporal pretext tasks were defined at the clip level. So which was like giving one label for a sequence. But we propose like more challenging tasks because it is well known that like if we throw more challenging tasks to the model, it helps it to learn like better features. So I mean, I'll walk through this. I'll propose one of the proposed temporal pretext tasks, which is called out of order frame localization. So first we select a frame as uh, yeah, from the video, we first select a clip, and out of that clip, I mean, select a frame for which selected for the replacement from the out of order. So for the out of order frame selection, we again look at into like a maximum window size from the selected clip and select any random frame and replace it with the selected index. So our model is asked to like solve this kind of task. It's like a binary classification, multi-level binary classification. We can say like where one indicates like out of order frame. So in the first task, we seen like it was focused on like ordinal information. Now we'll look into the speed of the video. So we vary skip rate between frame to frame of the sequence, like from a selected predefined classes. Like for example, this it could be we can skip like any number of frames from 1 to 4 or 8 between consecutive frames, and a model is asked to like classify them through a regular I mean cross entropy loss. So now putting everything together, like we'll see our overall framework. So first of all, we pass like each of the sample frame of the video to the image encoder. It's just a 2D backbone. And considering like each frame embedding as a token, we add like positional embedding to that and passing it through the temporal attention, which is like self-attention over like all of these tokens. We get like its frame-wise video representations. So this kind of, I mean, separable 2D and 3D convolution transformer-based model is called like VTN, Video Transformer Network, proposed in ICC 21. And on top of the output tokens, we can apply our pretext task. So starting with the first task called like out of order frame localization, which is basically taking like, it's just a binary classification using a binary classification, cross entropy laws, and it just identifies if the frame is in order or not after applying sigmoid on top of the output tokens. And taking the difference of these output tokens, we can get a notion of like the skip rate or like playback speed. And we classify each of the consecutive this kind of token difference into like predefined classes. And it is trained through like a cross entropy objective. So firstly, we will see like how our model performs well on action related downstream tasks, which is like a high level semantic understanding. And we, show results on like a series of like data sets like which is collected from internet videos or collected from like hand object interactions or in collected in like indoor control setting or like multi-label indoor actions as well. And we consider like three fine-tuning setting. One is linear classification, where we just train a single layer on top of the learned SSL representation, full fine-tuning, and like zero-shot video retrieval, video to video retrieval. So we can see on linear classification, our model is consistently outperforming all of the prior works, which is on full fine tuning, it gets like a very competitive performance right next to the video ME. And on the video zero shot video retrieval, it beats all other methods by a huge margin. So we can say our method is like absolutely state of the art on video retrieval and linear classification. So which is most desirable for like video search applications. And apart from actions, the method is also, works well and outperforms prior video SSL methods on multi-level entity recognition as well. For example, it could be like recognizing action, concepts, object scenes in like a multi-level setting. So previous tasks were more like semantically high-level tasks, recognition tasks, and now we'll see like our method is capable of solving like low-level correspondence task as well. So without doing any fine-tuning, here are our results on like video object segmentation. And Another, yeah, there are more results on like post tracking as well. So we have seen like, I mean, yeah, so in summary, our video SSL our main contribution was like breaking the shortcuts in the existing pretext task, and we proposed 2 more frame level temporal pretext tasks. We were able to achieve like a strong results on high level semantic understanding tasks, for example, action recognition, video retrieval, or multi-level classification. And also we were able to solve like low level temporal correspondence tasks as well, video object segmentation and post tracking. And so main key attraction of our method is that it doesn't require any full fine tuning after the self-supervised pre-training, which is required in like many methods like video MAE or like other contrastive learning based methods, and which is more suitable for like video search applications. And our project webpage is publicly available. So till this point, I have covered like Tickler, which was based on contrastive learning, and No More Shortcut, which was based on temporal pretext tasks. So both of these are like self-supervised learning paradigms, and we only dealt with the unlabeled data, learning on unlabeled data, and then doing the downstream task. So in practical setting, we know that like along with unlabeled data, we know some labels as well. So this kind of self-supervised learning paradigm, it doesn't provide like the best solution for that, we'll see. So to utilize a self-supervised model for like limited label setups, I mean, we can do it in 2 steps. So in the first step, it's like learning in the self-supervised way from unlabeled data and fine-tuning it on the label videos. So there is a problem with that, like a model loses its generalization capability while performing fine-tuning on this kind of label videos. So for example, if we look at the results of state-of-the-art self-supervised and semi-supervised methods, we see that our method like Tickler, it is like lagging far behind the one of the prior semi-supervised methods by like more than 10% relative on limited label setup. So it shows us that like, I mean, utilizing label data in using self-supervised, it's not the best solution. So a semi-supervised method, it is different and it is more effective because it deals with like both label and unlabeled videos together to train the model. So it preserves the generalization capability, and also like it is useful for dedicated downstream tasks. So with this motivation, we propose time balance in CPR 23, which is a semi-supervised action recognition framework. And so from Tickler, we have seen like 2 types of contrastive learnings, like instance contrastive and temporal contrastive. In instance contrastive, 2 clips are attracted from 2 clips from the same videos are attracted relative to the other clips. So it makes it like temporally invariant as we seen in the Tickler. And for the temporal contrastive losses, it repels these clips from the same video. So in a way, it was a kind of temporal distinctive method. So we have like 2 very different kind of self-supervised representation here. Now question is, how can we use this kind of complementary video representations to leverage in the like limited label setup? So to understand better, like let's try to understand their behavior on like fine tuning. So on the left, we can see like, yeah, so this is just a plot of like a class-wise performance difference of distinctive model minus invariant model. And on the left, we can see like distinctive model, it performs way better than the invariant model, and performance difference is significant, like 40% to the 5%. And on the right side, it's like the other way around, like invariant model performs better. So we see like clear difference in their behavior. And if we look carefully, like the videos on the left side, it's more like, complex action, like for example, javelin throw, which includes like first running and then throwing, and or like other actions like long jump. Or whereas on the right side, if we see like it has like more repetitive actions, like for example, fencing, like which is like fighting with swords or like playing with yo-yo or those kind of actions. So which is like atomic and repetitive. And in a way, like it makes sense as well, right? Because like in the complex action, we have like clear, I mean, clips from the same videos are very different visually from each other, and it makes sense to learn differences between them. And for the repetitive atomic action, like it makes more sense to learn the similarity between them. So to leverage like strengths of both temporally invariant and temporal distinctive models, we propose like a dual teacher student framework. So in this framework, like both of these teachers are like pre-trained in like using the self-supervised losses, like which I mentioned earlier, and then fine-tuning the limited level setup. And to leverage like their complementary strengths, we are proposing a more effective like a temporal similarity-based reweighting strategy. And yeah, we'll look into each component in detail now. So first step is like self-supervised pre-training of both teachers. So on the left, I mean, we know this objective from Tickler, like temporal invariant teacher, which is simple extension of SimCLR, and distinctive teacher, which is like temporal contrastive loss from Tickler. So now to combine like predictions from both teachers, we propose temporal similarity based reweighting strategy. So first from a video, we sample 4 consecutive clips, then pass them through like the self-supervised models to obtain their features and compute similarity of each of the pair. We can have like this kind of similar temporal similarity matrix, and we obtain like this kind of temporal similarity matrix from both of the models. And by taking average of both of the matrices and summing the non-diagonal elements, like it gives us like a single similarity score, which we refer to as like instant similarity. It ranges from 0 to 1, since it is like average of cosine similarity, and yeah, and we normalize that. So a low score indicates that like a complex action, and high score indicates a repetitive action. So we will see like by looking at the visual example here. So let's consider like this kind of action, and so we know like this is a repetitive action. So its instant similarity score should be high. So and it's just like visual proof of that. Like it provides a high score around 0.8. And I mean, it indicates that like it is repetitive action, and we should put more weightage to the invariant model. And considering the other type of video, where we have like relatively lower similarity score, and it indicates that like it is non-repetitive action, complex action, and we should put like more weightage to the distinctive model. So in this way, we combine them linear by just performing a linear combination, distinctive and invariant teachers prediction. So yeah, so that was our method about, and we compare our method on like various data sets. For example, standard data sets like UCF1 on HMDB and Kinetics 400. And we consider like I mean, most commonly used setting of 16 frames and 112 resolution for ensuring like a fair comparison. So first we compare it with the widely used like semi-supervised baseline, which was originally proposed for images. Then we evaluate like video specific semi-supervised baseline. And as I mentioned, like we can also compare it with the strong self-supervised baselines as well. And our method time balance, it outperforms all method like by, I mean, a healthy margin like across all data sets. And the same observation is also true for like other backbone with like more capacity as well. So in summary, like we propose time balance, which is a teacher-student based like semi-supervised method for action recognition. We utilize complementary strengths of like the learned self-supervised representation, which we have seen like in the previous chapters. And it provides like state-of-the-art results on 3 well-known data sets, and our code is publicly available. So problem with time balance is that like it performs really well on like coarse-grained actions, as we can see like from this videos. So which includes like a diverse scenario of like actions, like for example, where we can identify the action by only looking at a single frame as well, right? Like because it covers like a broad set of categories of action. Whereas in real life applications of action recognition, it often requires like fine-grained understanding. For example, these 4 diving sequence, they belong to different classes, and our method time balance, it's not able to classify them like very effectively. So to, I mean, deal with this kind of fine-grained actions, like we proposed fine pseudo in recently in ECCV 24. It got accepted by like with 2 strong accepts and like good reviews. So major difference with the time balance is that like it is based on the pseudo labeling framework, whereas time balance was on like knowledge distillation. And here we are proposing temporal alignment based verification metric learning and collaborative pseudo labeling strategy. So it sets new state of the art on 4 fine-grained action recognition data sets, and it also gets like competitive results on well-known coarse-grained action data sets as well. And for the first time, we evaluate and like it outperforms all methods in like open world scenario as well. So yeah, so first, like let's understand like what makes fine-grained action recognition particularly challenging compared to the coarse-grained actions. So I mean, so some major part is the notion of like action phase, which is part of the action. It follows like a deterministic order, like following laws of physics. And so let's understand by this example of diving. So in this diving action, we can see 3 phases occurring in like some specific order, which is shown in like different color segments. Like so, first phase is like in diving, like takeoff, then in flight, which is like I mean taking twist in the air and like entering into the water. So and yeah, we have like another action class as well. So which includes like different action class. So important thing here is to note that like only change in like one of the phases, like which is like only small part of segment of the video, it changes the whole action class itself. So this kind of so in this particular example, we see like a person is entering while facing the water, and which was like previously it was like looking upwards. So only the single change, it changes the whole action class, and this makes the find and action recognition more challenging to take decisions based on action phases. So let's take a toy example of binary classification where we given a pair of videos, we need to identify if the pair belongs to the same action or not, or it belongs to like different action classes. So if we consider like, and this different color segments again, like it includes, it shows like different action phases. So if we take like the standard distance function, like let's say cosine similarity, we see that like it's not producing like the discriminative score between the pair of the same action versus different action. We see like it produces almost like similar scores, and yeah, so it's not producing like effect. I mean, useful, meaningful distance. So a more meaningful solution would be to align the action phases first. Like for example, as we know, like this matching the action phases shown in different color, and after aligning them, then we compute the distance. So it makes more, I mean, meaningful distance score, and it gives us like a more discriminatory metric as well. So this is our, I mean, key observation, and we will leverage that into our overall framework. So now we want to utilize the alignment distance to classify the find and action classes, right? So one way to compute alignment distance is through dynamic time warping, which was like very well-known method previously. And so in that, first we construct temporal similarity matrix from the 2 videos. So which is just by taking the cosine similarity for each timestamp, and we can have like this kind of matrix out of that. And uh, after computing this kind of temporal similarity matrix, I mean, we just look into the local neighborhood of like neighboring pixels and take the minimum path. And in this kind of greedy approach or like dynamic programming process, we get like the minimal costing path, like from one video to another video. So, and by aligning, we get like some optimal path cost as well. Now, problem with this kind of optimal path cost is that like it depends on 2 things, and which is one is like video length, and another is visual similarity of the videos. So these 2 factors make it not, I mean, practical to use it for like to identify the action classes. So we propose for that we propose a more learnable distance. To build the learnable distance based on DTW, we propose a metric learning based approach, and I will walk through step by step. So first, from the label set, we sample a triplet, and where anchor and positive pair consist of the same action class, and negatives are coming from the different action classes. And passing each video through the frame-wise video encoder, we get the frame-wise video embedding. So T indicates like the number of timestamp, and F indicates feature size. And yeah, so after that, like we utilize this frame embedding to compute the DTW distance. And to be more specific, like we are utilizing a differentiable version of DTW called soft DTW, which is like good for like GPU implementation and make it and backpropagation possible for GPU computation. And in this way, like we get the distance for like anchor positive and anchor negative. And after computing this distance, we can compute triplet loss with some margin, which is like a regular formulation of triplet loss. So this kind of triplet objective on top of the alignment distance, it encourages model to focus on, like action phases first and discriminate the videos based on the action phases. And our second learning objective also scales the distance to a meaningful range from 0 to 1. And it first maps the distance through the MLP and then applies sigmoid and then applies a binary cross entropy loss where 1 indicates like the same action class and 0 indicates like the negative distance to 0. We set it to 0. So till this point, we have learned like only from the label data. As we have seen, like we only utilize the label set here. Now we also want to utilize unlabeled data as well to leverage that through pseudo labeling. So first sample like one of the unlabeled video from the set and pass it through the alignability indicator, which we learned from previous step, and get their frame-wise representation. And meanwhile, we already have such frame-wise video representation for like label set. Like we stored it beforehand and in like a dictionary. And now we compare like frame-wise embedding of, distance from this unlabeled video and this label video, so that we have like class-wise similarity for each of the label sample, and assign the class prediction based on the relative similarity. So let's say we have like 48 classes in the label embedding. So we first compute their similarity with the unlabeled videos, take their average, and apply the softmax to get the class prediction out of that. So in this process, we have not used any classification layers. So that's why we are calling it like non-parametric classification. And we also pass the unlabeled video through the regular action encoder as well, and get their class prediction. So, and finally, we combine both of the class predictions to get like a collaborative pseudo label. So this kind of particular, approach, it's successful because in a way, like we are combining a global understanding of video through this action encoder, which treats like video as a whole and like provides just a single prediction based on like the overall spatiotemporal understanding. And the alignability indicator encoder, it takes decision based on the local observation, which is like action phases. So it aligns the action phases first, and based on the alignment distance, it provides us some score. So we have like kind of complementary understanding, and this makes our approach more successful in refining the pseudo label from the unlabeled set. And we provide results on like 4 well-known fine-grained action data sets called diving 48, FineGym 99, a more challenging version of FineGym, which consists of 288 fine-grained actions and fine diving. And compared to, similarly to time balance, we also compare with like video self-supervised methods, traditional semi-supervised methods, and video-specific semi-supervised methods. And we see like huge improvements compared to the all prior methods across all protocols. And we also report results on 2 coarse-grained action datasets as well, which are like widely used, called Kinetics 400 and something V2. And to ensure like a fair comparison, we kept the same model parameters and model initialization and the backbone, and same number of floating point as well. And we can see like our model performs very competitively or slightly better than the prior methods on 2 different architectures. Now, all of the previous semi-supervised methods, they were only focusing on a control setup, where our unlabeled samples were having classes from the known classes. Like, it was not the practical setup for like a semi-supervised method. Whereas in open world scenario, we can have like unlabeled samples from some unseen class as well, which we didn't see in the label set. And our goal is for semi-supervised learning is to discard this kind of novel classes during the pseudo labeling process to reduce noise. And we report results on like diving data sets where we treat 40 classes as the seen class and 8 classes as the novel class. And it is interesting to see like the prior semi-supervised baselines like pseudo labeling or UPS, they degrades the performance of the original baseline without using any semi-supervised method. This is due to the fact that like it introduces noise during while performing the pseudo labeling. It degrades the performance. And our method time balance, yeah, and our method find pseudo, it performs like robustly and like it gets the best performance on open world scenario. And so the main reason behind the success of our method on performing well on open world is that like we were utilizing the non-parametric classifier while performing the pseudo labeling. So it makes our method like I mean independent of like making class predictions like so yeah. And so in summary, like we were the first work to like introduce like semi-supervised setup in fine-grained action recognition, where we propose alignability verification based metric learning and collaborative pseudo labeling strategy. And our method performs like state of the art on 4 fine-grained action recognition datasets, and it also performs competitively on known coarse-grained action datasets. And for the first time, we evaluated on like open world scenario, and more results and like code can be found on our project webpage. So yeah, so till now we only focused on like improving the performance from the label in a label efficient manner. But in a practical setting of action recognition, for example, in this video, we can see like a application where like application is to monitor like an elderly person to recognize actions like eating, laying down, or taking pills. And since we know like edge computing, it's still like not very mature area. Videos are shared to the computation cloud. And while doing that, we end up sharing a lot of private information as well. For example, gender, skin color, clothing, which is like quite undesirable and unnecessary to recognize the actions. And so till this point, we've seen like 2 self-supervised methods and 2 semi-supervised methods, but none of this like it deals with the concerns of like privacy leakage. So to address that, to address like the raising issues of privacy preservation, we propose SPACT framework, which was published in CBI 22. Yeah, so let's review like the existing approaches of the video anonymization. So our goal is to anonymize this video in such a way that like it remains, I mean, it produces like a meaningful feature for action recognition model while effectively removing like the private sensitive information, for example, skin color, gender, or clothing information. And another requirement is that this kind of annotation we try to avoid during training because it's infeasible to train video frame by frame at a larger scale like this. So looking at like in the literature and the first set of methods, it involves like simple downsampling. So which is where videos are like reduced in the resolution, and it's just like simple using like low resolution videos, but we can still see like a lot of private information here. So in a way, it defeats the purpose of like stopping the privacy leakage. Another sets of method, they use like a pre-trained object detector, and using first they locate the private attributes in the video, for example, like person's body, and it obfuscate like the detected region using blurring or like this kind of whitening operations. So we can see like, I mean, we can't really see the action region here. So it defeats the purpose again, like of like maintaining the utility performance. So there is interesting work like using adversarial training framework and from like Wu et al. It utilizes this both action label and private attribute labels to produce like a more effective method. And sorry, so they are able to maintain the utility performance as well as they are removing the privacy features as well. But the only problem is that they need this kind of like private attribute labels, which is again like infeasible to train at like larger scale. Whereas we propose a self-supervised method, which doesn't require this kind of private attribute labels, and it performs similar to this supervised method. So we call it SPACT framework. We'll cover that like. So to formulate like problem of like privacy preservation, action recognition, like, I mean, I'll keep using this kind of notations, like where FT represents like a utility branch, which is nothing but action classifier. It could be like 3D CNN or video transformer model, and a budget branch, which is like a attacker's model, which is again like nothing but a privacy classifier based on 2D CNN or like any classifier model. So our first criteria is that after applying the anonymization function shown this FA, the loss function of the utility, it should remain similar. So it makes sense because we don't want to drop the utility performance like after doing this kind of privacy preservation. And secondly, this anonymization function, it should increase the loss of the budget branch, which is like while classifying the private attributes, it should produce more loss. So in a way, like it is preventing the private information leakage. So starting with the first part, like our, which is anonymization function, which is like heart of our method. And it is nothing but an encoder decoder based unit model. Second component is like utility branch, which is nothing but 3D CNN or any video action model. And privacy or budget branch, which is a 2D classifier model. And putting everything together, here is how overall framework looks like. And so now before starting the proposed Minimax-based optimization strategy, I'll just try to make some notes on initialization of each components. So the anonymization function, it is initialized with the identity function. It means like, it just gives like whatever it takes. Like, so it's it's just identity function. Like it produces the private attributes uncovered. And our second branch, utility branch, it is pre-trained with the regular large-scale pre-training of action recognition model. And the privacy removal branch, it is pre-trained with the regular contrastive and self-supervised objective. Like in our framework, we utilize BOL. And to optimize our framework, we utilize a minimax optimization strategy. So first, we take the initialized models, FA, FT, and FB, and we keep the FT and FB frozen and FA in the learnable mode. So our now idea is that like we want to decrease the this regular action recognition loss, and we want to increase this kind of contrastive loss. I mean, contrastive self-supervised loss. So in a way, like, what do I mean by increasing the loss? Because like I mean, the self-supervised loss, it indicates like a similarity between two frames of the video. So if we increase the loss, it means we are reducing the similarity in the learned representation. So in a way, we are destroying like the unnecessary spatial cues like from the videos here. So this lower branch, it destroys like all of the spatial information, while the upper branch, it preserves the whatever meaningful for utility. So in this way, we train our model, and it was the first step. And to prevent the trivial solution, we also keep updating the FA and the FT and FB model as well in the second step while keeping the FA frozen. And so to better understand this, like we can set some analogy with GAN model as well. So where FA can be think in terms of like a generator, FB can be think in terms of like a discriminator, and FT, it's just nothing but like a constraint. So in the first step, like FA tries to fool FB. And in the second step, like we update the FB to make it more stronger to, I mean, which encourage FA to produce, you know, like more noisy or like anonymized outputs. So since there are like two objectives here, like we show the results in terms of like trade-off plots, where on the y-axis we see like the utility performance action recognition, which is higher is better. And on the x-axis we have privacy, which is lower is better. So ideal point should be on top left. And we see like on various data sets, our model, this shown in this red star, it's able to achieve like close performance to this supervised model, as we can see like across different protocols. And on the novel private attributes, for example, like let's say if we use it in the training set, like attributes like human related privacy, like skin color, gender, or those kind of privacy attributes. And our downstream task, it includes like private attributes like scenes or like objects, which is again like leaks the private attributes. So in this kind of like generalization task, we outperform the super method by by a good margin. And here are some output videos across different methods. So considering this input video, which reveals like all of the information of the person's private attributes. Here are like different outputs from like different methods. So our method, we can see like we can't really tell the like skin color or like any those kind of private attributes from the action, even at the human level inspection. So in summary, like our contribution like was to like highlight a self-supervised privacy preserving action recognition framework where it gets like a competitive performance in terms of like scene action classes, and it outperforms all prior methods and sets new state of the art on like novel uh, uh, unseen generalization. And our code is publicly available, and we also filed a patent on that. And so yeah, to summarize my dissertation, it was focused on two major aspects of video understanding. One was label efficiency, where we propose two self-supervised methods and two semi-supervised methods. So this was only dealing with the improving performance in terms of label efficiency. And another aspect, it's like privacy preservation. So starting with the tickler, we introduced two temporal contrastive losses. Tickler very effectively on high-level complex downstream tasks, for example, action recognition or video retrieval. However, I mean, as we know, like it didn't work well on like low-level temporal correspondence tasks, for example, video object segmentation. And to address that, we propose another work, no more shortcuts, where I mean, we propose like uh, we mitigated the shortcuts in the existing pretext task and proposed more challenging frame-level tasks. And we demonstrated that like our model was able to achieve good performance on both high-level and low-level temporal correspondence tasks as well. So, I mean, both of these approaches like only focusing on like the unlabeled data sets. And in the practical setup, we also have like some small labeled data set as well. And for that, we propose a semi-supervised framework called time balance in CBI 23. And it was based on capitalizing strengths of the self-supervised methods, which is invariant and distinctive teacher. And its major benefit is that it sets like strong results on coarse grained action data sets. So although this doesn't work well on fine grained actions, like to deal with that, we propose fine pseudo framework in ECCV, and it leverages temporal alignability to take decisions based on action phases. As I mentioned, like action phases is more important in taking discriminating the fine grained actions. And it achieves like it sets state of the art on 4 fine grained action recognition data sets. And for the first time, we evaluated for open world scenario, and it performs the best on open world scenario as well. And finally, to prevent the privacy leakage, we propose PACT in CBI 22, where we didn't need any label information of the private attributes to train our framework. It performed like competitively on the known action private attributes, and it achieves the best result in terms of like generalization on unseen attributes. So there are like many open research directions based on our dissertation. So in self-supervised learning, the context of finding shortcuts in typically we assume that like unlabeled videos are like versions of Kinetics 400, which is again like a curated data sets, you know. So all of the self-supervised method, they use like unlabeled version of the Kinetics 400. So which is in a kind of like underutilizing the true potential of self-supervised learning, because its potential is to learn from, its main purpose is to learn from unlabeled, uncurated, longer videos. And in the context of like finding shortcuts in the self-supervised framework, we could also look into like other learning paradigms like mask image modeling or contrastive learning. In semi-supervised learning from videos, we introduced student-teacher framework, but we needed to fine-tune the self-supervised teachers, you know. So while performing the fine-tuning of the teachers and then distilling their knowledge of through the class predictions, like it's a kind of ineffective because it loses the generalization. So more effective and better way could be using the contrastive self-supervised distillation. And additionally, like there is like lack of dedicated research on like open world semi-supervised action recognition, and which could make like action recognition in semi-supervised setup more practical. And in terms of privacy preservation, one promising direction could be extending the anonymization function to the multimodal setting, which could be like video language modeling, or also like preserving the necessary spatial information, because in this pact we destroy like all of the spatial information, right? So more meaningful approach would be used like in a collaborative downstream utility, and which also which could be useful for like temporal correspondence task as well. So yeah, I could cover like these are like some of the papers from my published during my PhD, and I could cover like 5 of them in this dissertation. So there are like other are also relevant to video understanding, and which includes like 8 CS ranking conferences and 1 oral paper presented at ECC recently. Yep. Thank you.